based on a theme. So I'll start up with some. So let me take up this problem where some data have been given to you. I'll read this problem for all of you. He has said that you have to consider a hypothetical wave pulse. And this pulse is given to you at the time instance t is equal to 0. There is a complete pattern. I mean, if you look into the shape of this pulse at t is equal to 0, they have specified that completely, that I will draw afterwards. And the main information is that he is letting the pulse travel leftwards, right? And the speed is also given, 2 meters per second. There are few informations that we need to predict. If you look into the question carefully, the things that we have to answer are of different kinds. Like in the first option, he's talking about the y coordinate versus time for a specific position, that is x is equal to 0. You read this carefully. This coordinate is x is equal to 0. How does the y coordinate, that is the disturbance, at that position vary with time? In the second point, it is obviously the Vy. This is indirectly the particle velocity at the same location, that is x is equal to 0. If you look into the third part of the question, he is demanding about the wave shape, that is y versus x at t is equal to 0. And finally, he is talking about velocity, that is the particle velocity Vy versus coordinate, x coordinate, at t is equal to 0, at the instance t is equal to 0. So if you look into this traveling wave, what we will do here is, at t is equal to 0, let us try to analyze what is happening exactly, and we'll try to find out the energy of this wave also as an additional counterpart to this question. So let us just try to observe this problem at t is equal to 0. He's saying y is equal to 0 for x less than 0. So maybe this coordinate is our origin, x is equal to 0. There is no disturbance here on the left-hand side. Y is equal to x by 2 for x lying between 0 and 2. So again, it is a straight line from 0 to 2, right? This coordinate here will be equal to 1. Y is equal to 3 minus x for x lying between 2 and 3. So that makes it straightforward, because at x is equal to 3, it will be equal to 0. And afterwards, for x greater than 3, there is no disturbance. So again, it is flat. So this is the wave shape, like flat, horizontal, this part, the third segment, and finally it is a horizontal part, right? Now he's also saying that this wave is traveling in the negative x direction. So it is moving leftwards. And the wave speed as such, v, that is 2 meters per second. Now we need to address few issues in the problem, right? Okay, so first part, let me answer. You have to find out y versus t at the position x is equal to 0, right? This is the point. So one thing we all understand, that if you talk about a traveling wave, which has got any equation of the format f of ax plus bt, you can find out that relation between the particle velocity and the slope. So generally, I'm saying if this wave is moving in the leftward direction, you understand that ये segment जो है, this has got a slope of 1 by 2, right? And the second segment here, it has got a slope of -1. So fine. So as the wave is traveling leftwards, if I look at x is equal to 0, this segment will be present at this location till the wave travels a distance of 2 meters. So till the time instance is 1. So that makes sense to me, 0 to 1. And if that slope is constant, right, this part will be traveling leftwards. Like if the slope as such is constant there, so particle is moving with Vp as such will be equal to negative of that wave velocity, which is coming out as -2. And slope here is again 1/2. So this value is coming out as +1 here at x is equal to 0 till 1. And you can see, 1 second, 1 meter, so slope is 1. And for the second part, again, the slope is -2 because particle velocity as such is -2. So you can see here 1/2 -2. So A is correct. That is indirectly a derived counterpart of B option of the problem. Further, what is happening? At t is equal to 0, as far as the shape is concerned, I have already drawn that shape. That is y versus x. This is y versus x at t is equal to 0. So 0 to 2, it goes up to 1. 2 se 3 mein, it is coming down. So I don't think this is the correct option. The shape is not right. And finally, he is talking about particle velocity versus x coordinate at t is equal to 0. I think if you look into the curve only from here itself, at this specific instance, all these particles are having 0 slope. So particle velocity is 0. I'm talking about D part of the problem. So we understand that this is 0, right? From 0 to 2, we can find out the slope is constant. So particle velocity +1, that will be constant. 2 to 3, it will be -2. And finally, again, 0. So I think it is 1 for 0 to 2, 2 to 3 -2. And after 3, again, it will come out as 0. So that simple relation for a traveling wave, where Vp was equal to minus of wave velocity with sign into slope, that will help me to infer that results for this problem must be A, B, and D. So these three options will be correct in the problem. To find out energy of the signal, if you read this problem again, and they can give you any such function which is bounded continuous function. Like in this case, if you look again, it is a triangular wave pulse, and they've given you the shape at t is equal to 0. Let us just try to observe it. This is the triangular pulse. Equations are given. The point is, if this pulse is moving in positive x direction, string tension is given, mass per unit length is given. We need to find out the total energy which is present in the wave pulse. I think all of us understand that for any wave signal, if I look into a dx segment at any t is equal to t, if you want to write the decay energy that is present there, it is half of mass per unit length, mu. I'm representing mu into dx. So mass there into particle velocity. So that term will be dou y by dou t the whole square, right? And if I want to write the differential potential energy du, so that comes out as how, again, it is half of mu dx multiplied by dou y by dou x, the slope of the wave at that particular location, dou y by dou x the whole square. I'm using that mu because I want to use the proportionality actually. If you want to write the exact formulation, I can write it exactly also. It comes out as half of tension into dx into dou y by dou x the whole square. Right, that term actually becomes v square mu, and I wanted to use that proportionality here, but fine. So these were the two relations that are required in this problem. If we just go through this problem carefully, what does he want me to find out? The total energy which is present in the pulse at the given instance, let's say. Let's say with time also, if the pulse is traveling at any t is equal to t, for the same shape of the pulse as at a different location, the total energy in the pulse will remain the same. So it doesn't matter that I'm calculating it at t is equal to 0 or general t is equal to t, right? So let us just try to write the expression. What is it coming out as? Now, I just want to find out the value in the first segment. Let's say, if you look into the information, this value here is coming out. This is a by 2, right? This value is m a by 2, right? And these two like congruency hai. So if you want to find out the energy in this segment, rest we can easily write. So what I am doing is, at the same instance t is equal to 0, I want to take a general element and I want to write the term. So the total energy dE I want to write at that location in that element. So what I am doing, going to a general x, cutting a element dx there. I want to write the total energy which is concentrated in this segment dx. So what is that coming out as? Let us see. So it is half of mu dx into. Now I need that term. Already they have given you that the wave velocity v here is root of tension is given, mass per unit length is given. So that term is T by mu. That is our first equation, right? So if I observe the particle velocity for all these people from 0 to a by 2, right? I need the square term. So as the wave is also traveling in the positive, so fine. It is negative of, use the wave velocity v, and the slope as such is m, the whole square. And if I want to write the second term, it is half of t I'm writing as v square mu dx, and slope obviously is a constant here, so so m square, right? So just try to integrate this expression from x is equal to 0 to x is equal to a by 2, right? You will get the energy which is present in 0 to a by 2. And remaining segment, if you talk about the energy, slope there is same, so particle velocity will also remain the same. So I'm convinced that the total energy should be equal to twice of this expression, twice of this. Overall, you can take twice of whatever integral I'm writing in averages. And basically that will become straightforward because this 2, all this will cancel out. It is mu v square m square. And simply it is twice of dx, so 2x, and that term will become a by 2. So technically it should come out as mu v square m square into a, right? And in terms of the given parameters, mu v square, like that v is t by mu, so mu v square term that can be replaced by t. So we are getting that term as t m square a. If you just observe it carefully, you should get this term, this as what, m square into tension into that constant a. So ultimately, whatever be the shape that he is trying to give me, if he wants me to find out the energy, we can integrate that expression with appropriate functions and we can find out the potential or the kinetic energy. I mean, the rate, at times when we have to write the expression for the rate at which the energy is getting transmitted from that particular location, that time also we think the same way. I mean, at that x, when we cut a dx and we write dk and du, that is the net dE, and the rate at which it is changing is indirectly also the rate at which the energy is getting transmitted or passing from that particular cross section, which can obviously help us to find out the expression for the power, the rate at which the energy is getting transmitted from that cross section. So in any other problem, if that is also required, we can derive the expression using the same results, right? And we understand that y here is obviously a function of x and t. So when I'm talking about the passage of energy from a given x, so whatever dE I will write, we will finally try to observe that dE as a function of t, right, at a given cross section. And that dou E by dou t, you can say dou E by dou t, will serve the purpose. That will also tell you the power transmitted from that particular cross section. All right, so let's build up on this small concept and try to answer this problem. In this case, they have given you two strings A and B, length 4L, L respectively. Mass of the strings is same. So basically, he's trying to explain the rarer and the denser medium in this case. If you look into the proposition in the problem and look into that interface from where it is getting refracted as well as reflected both, he wants you to tell about the exact wave shape after transmission or reflection. Other than the amplitude, which we can write using the Stokes theorem. If I have to just check into the shape of the signal, we understand that there will be a phase change for the wave, which is getting reflected. And for the refracted signal, phase will remain the same. So that will help you out predicting the shape of the signal. So obviously, this is not possible that all these signals which are having Y positive after reflection, Y stays positive. That's not possible here. Out of these three, we can see. Also, if you look into the order of the slope, the way the signal came up to this point, right? So, I mean, you understand that whatever Y reaches this point and gets reflected, the order in which the signal will be reflected back will be the same as the order in which it reaches this place, this point of this interface, rather. So this does not seem correct again. This cannot be the order. This will be reaching last at this place. So fine, these two may work. Now we have to predict, like, if you look into the shape of the signal in the front side, that is similar to what is given. So again, I am not happy with the C option here. Just check in third case. So this will be quite evident that only on the basis of the property that refracted signal will be in the same phase as the incident one, and the reflected will change by a phase of phi by Stokes theorem, we can predict the output signal here. If we have to write the amplitudes also, that also can be written with the help of the formulation, because in this problem he has not given, although we know the V, the ratio of V can also be written. So if we need the exact ratio of the output signal and the incident one, we can write that. But I don't think it is required, because only on the basis of the phase also you can report the result. Problem which is based on these few principles that I have discussed with you. They have given a snapshot graph of instantaneous velocity of the particle on a string, and he has already given that this wave is moving towards the left direction. So if you look into this, it is Vp versus X, right? And you have to like find out the Y versus X graph of the wave at that very instance. If I use the basic concept of the traveling wave, I think you should be able to, Vp is known, and the direction in which the wave is moving is also known. It is moving in the leftward direction. In fact, even without looking into that, from these four shapes which are given to you, we can also predict it, because it was negative of wave velocity, and wave velocity in this case is also negative. And then I have to write down the slope. So ultimately, it comes out as something which is of, I mean, sine, if I look, the sine will be same as slope. And obviously, I need that term, which is the wave speed. So practically, I have to look into the slope and I have to look into the wave speed. That will help me out in finding out the particle velocity here, right? This negative I have taken as I know that this wave is moving in the leftward direction, and that wave speed is again behaving like a constant. So slope should be constant, because particle velocity is constant over this x period. So slope should be constant. Again, it is constant to slope. So basically, the composition is of two slopes which are constant. And now the only problem is particle velocity has got a higher magnitude, negative, but got a higher magnitude here in this domain. right? So slope should be higher there in terms of magnitude. So now I think looking into this much information, you can infer. Only thing, if you take into consideration, like this is not possible here. This may be possible. This is again not possible. And now out of A and C, A seems to be correct. You can see here, just on the basis of slope, I am saying that. Because slope should have been positive in the first segment also. You know, wave speed is a constant, so VP should be positive. Only that much will serve your purpose. Magnitude of slope, obviously, I've seen because particle velocity magnitude, I know. So we can predict on the basis of. Now, in the next problem, he's talking about a situation where the wave is not traveling in a positive x direction or standard. It is not a standard case. It is moving in some direction in a plane which is not the plus x or the plus y direction. Now, it is quite clear in this problem. He's talking about a plane progressive harmonic wave which is having this equation, right? This disturbance phi is given as phi max sine of 2t minus 3x plus 4y plus pi by 3. xy in meters, t is in seconds. Now he says in the question, if n cap is the unit vector in the direction of the wave propagation and v is the speed of the wave with respect to the wave medium. So there are few things we need to answer in this problem: the direction in which this is traveling and the wave speed with which this wave is traveling. Now, if I generalize this, I try to rewrite this. Actually, that y or disturbance can be written as some maximum disturbance, some sinusoidal function you need. So when I say you write sine omega t minus kx, we can also use something called upon as wave vector, where we can write that term as k dot v. When you write this term as omega t minus kx or plus kx, let's say you're discussing a wave which is traveling in the positive x direction with wave velocity v, and you use something like a sine omega t minus kx plus phi. We understand that this term as such is the dot product of wave vector. This term kx, इसको ऐसे दिखाता हूँ. Observe it like this, like it is 2t minus thrice of, I am writing this term as x minus 4y by 3 plus pi by 3. I mean, you can observe it like this also. Now, x minus 4y by 3 is equal to 0, right? I mean, if you look into this equation, y is equal to 3x by 4. I'm not saying this is the direction of propagation. I'm saying when we write such equations, this term where is equal to 0, the direction of propagation of wave is along the normal to this term. I mean, x is equal to 0 here represents the normal to the direction of propagation, right? So similarly, x minus 4y by 3 is equal to 0. This is the line equation, y is equal to 3x by 4, right? And this angle I have taken as 37 degrees. So practically, the direction of propagation of this vector is this, which is normal to that line, which is coming out of this equation, right? X minus 4y. So this angle comes out as 53 degree. And again, so this is the direction of propagation. If I want to write this n cap, it will come out as it is 53 and 1. So it's coming out as 3i cap and minus 4j, right? This direction, 3i cap minus 4j cap, unit vector, so divided by 5. So n cap, I understand, we can find out. Now, the second important thing here was, what is the wave speed in this problem, right? So that's what I was trying to tell you. If you look into the unit vector of this term, here also, if you look into that vector, this was minus 3 I cap and plus 4j cap. So practically when I am trying to write it as, you understand, minus k dot v. So this term then got converted into minus of that term 3i cap minus 4j cap, whose unit vector I have written here while the wave is being propagating in this direction. And when you talk about wave velocity, v, in this case, all of us know that the k will be equal to omega by v. So v, that wave speed v comes out as omega upon k. In this case, omega as such, again, I'll write the same thing. I should say it is k vector mod, we can say k. Omega even in this problem is 2. If you look about into k, so that k basically represents the magnitude of that vector, right? Not the unit vector. Unit vector I have represented only for the representation of direction. Ultimately, this vector has got a magnitude of 5. So you understand that wave vector in this case, I could have said that this is wave vector mod. And wave vector here, or you can say apparent wave vector, whichever way you have studied this point. Ultimately, what we are trying to say is the unit vector in which the wave is getting propagated is actually a direction which is normal to that line, which is representing a term like x is equal to 0 here, which was a y-axis, which in this case is the equation of this line, right? And once we are done with this, I mean, basically I'm saying we are using transformation of coordinate, whichever way you interpret. Somebody can say we can rewrite our x prime and y prime here, and then we can express this equation in terms of prime. And then I need not do anything. I would have written k prime. And n cap here was 3i cap minus 4j cap upon 5, right? So C in this case will be your correct result. In this case, I am more interested, like if you look into the pulse, they're giving you a pulse which is starting at t is equal to 0 along the positive x direction on a string. The shape of the pulse is given. So that's fine, right? F and X are in centimeter. Linear mass density is given 50 gram per meter and tension is given 5 Newton. Now there are a few things we need to find out. And more important, I'm interested in the C and the D segments. So energy of this pulse that you can write now, right? I'm not looking into the interaction of pulses. So the pulse here from -4, x is equal to -4 to x is equal to 0. Then from 0 to 1, it is minus x plus 1. 1, and then here. And here it is 0, 0, it is 1 again. So the only thing is the slope is a bit different. So that is how the pulse was to begin with. So just look into C and D parts of the question and try to answer it. Everything I'm using in CGS only, right? And the rate at which the wave is traveling, that is known to me. V in this case is tension, which is 5, and mass per unit length. So that was 50 upon 1000. So it is actually 10 meters per second. That is the pace at which the pulse is traveling in the positive x direction. So if I just want to write the transverse velocity, x is equal to 13 at t is equal to 0.015. I mean, there are only two things which are coming to my mind. And luckily, they have also given values which are like similar. Only thing that is coming to my mind is if this wave was traveling in positive x, so particle velocity at any point should be, just look into this. What is the value which is coming out? So two possibilities I'm trying to write. Negative, this value here is 1. So slope is like -1 and particle velocity is 10. right? So the transverse velocity, the particle velocity, will come out as 10 meter per second. And in the second case, it will be 1/4 of that. So that comes out as 2.5 meter per second. So the thing is, the only concern for me is it will be, if the answer can be 250 minus 250 centimeter per second, if we can see that this section has entered there, and already you are saying that it is traveling with 10 meter per second, and you have been given some time for which it has to travel. So just look into the distance along the x direction that it has traveled. In this case, in seventh problem. X is equal to 13.
Switch off. All sevens are good. All sevens. All sevens. If
you cross-check it carefully, x is equal to 13. At t is equal to that time velocity I have given you already. So if you check that which segment of this pulse has entered that location, x is equal to 13 centimeter, you can easily verify that the second section, that is this segment AB, let's say this is segment AB, this is AC. AC segment is one which has entered that tenor. So C option seems to be the correct result, right? That is simply on the basis of the distance that it has traveled L, right? So I've just multiplied the wave velocity with time and I have checked how much it has traveled. And x is equal to 13 centimeter is a location which is being overcome by this segment of the signal AC or this segment of the signal. So if you verify, it will be the segment AC. That's why I'm saying C option will make sense in the problem. And as far as A and C is concerned, that is quite simple because we know the shape of the pulse. So area enclosed won't be a H. That is something which we can easily find out. So some different signal given to you and you want to find out the wave velocity there. Here you have been given a string OP of length L. He is saying that the string is fixed at both the ends and it is vibrating in the first overtone. Right. So maybe something of this sort, that it will be forming two loops here. I don't know the shape of the signal at t is equal to 0. So we don't know the location of the string at t is equal to 0. These are the boundaries that I have. So that he has given. And antinode amplitude is given to you. So that is given as 8, right? Let's see. Now he's saying at some time instance, the shape of string is shown in the figure. So fine. And points O, C, and P represent the node. So let's say this is O, C, and this point is P. They are representing the nodes. Everything is known in this problem. These are midpoints. So OB is equal to BC is equal to CD is equal to DP. That's fine. BQ distance and DR distance, antinode amplitudes, that is. So you have to choose the correct, multi-correct options are there. So we need to be careful. Now, this is something where we need to do some derivation because, or directly if we have derived, we can use the results also. Like he is talking about the flow of energy through the sections, right? So he's saying that if on this string at some instance, let's say I would have taken a point S here, and we are very clear that at some point of time, let's say at t is equal to 0 only, all the particles were moving upwards. So the signal would have been flat with these points having different velocities and maximum being at B. The complete shape of the string would have been a straight line. So we understand that in this standing wave, at a specific instance, like I will just try to draw this. This is 0. And then again, I'm talking about these velocities. Right. So this is that. So if that instance I'm taking as t is equal to 0, we know that the potential energy throughout would have been 0. You understand this point that by using the equation of standing wave, we can justify this fact that, I mean, if you take y is equal to any such equation, I'm using a as my antinode amplitude. I'm using a simple equation, maybe a sine kx, and take any sine omega t plus phi, doesn't matter, right? And just for the sake of simplicity, I'm saying if this was x is equal to 0 and this is x is equal to L, right? K I need to find out here. K term will come out as 2 pi by L. So we know the location of node, antinode, everything. So what we are trying to find out here is the net flow of energy through section is dependent on time, in which sections, and constant here. So let me use the result first, then we can obviously derive also. Through section OS is dependent on time. That is the first statement. Through net flow of energy through OQ, the section OQ, the length OQ you can say, is dependent on time. This we are very clear that between a node and an antinode, whatever energy is present, that is constant, right? The same is true for the energy which is present between two nodes. So when you talk about OC is dependent on time, that is also wrong. Now, when he talks about flow of energy through section OT is dependent on time, varying with time, how come? What is the function? I'll write that. And OS, these are kind of similar. And obviously, if I say that B and C statements are wrong, A is correct, D is a direct inference of that. And as far as that energy variation is concerned, so the best way out is and this result is independent of that phi. So you are writing y as some function of x and t. And the thing is, if you want to write that energy in that segment, just write the energy of expression uh, of that segment as a function of time. And then you can check in a given segment, in whichever segment you want, in a given segment, right? So when I'm making a statement about node to node or node to antinode, actually, this is the result which we have derived, and on the basis of that only we are commenting. Generally, also you can ask about the energy present or the energy which is passing. So actually, you have to look upon the variation, right? So the same expression you have to use. The only thing, I'll just write that expression and then you can obviously analyze. So I'm writing that half of mu dx, that term, that is the mass, and then I am using that term dou y by dou t, the whole square. So that comes out as a sine of 2 pi x by L, and then a term omega, and that it becomes cos of omega t plus phi, right? And the potential energy segment again, term again in that segment. So it is half of t dx. So I'm using v square into mu into that term dou y by dou x, the whole square. So it is a k cos kx. Let me substitute k afterwards, and sine omega t plus phi, the whole square. So in the dx segment, I am writing this as my energy. So now we are very clear that in every dx segment located at a given x, the energy is a function of the energy present in that segment, the differential energy, you can say. That is a function of location and time, right? So if you are trying to write that energy at a given instance t is equal to t, so given t is equal to t, and you want to write the energy present in that stretch, so you have to just integrate this expression from whatever x is equal to xi to x is equal to xf, right? Just say if you want to analyze the energy between those two nodes, Remember, there are other ways of looking into problem also, but I'm just trying to explain the basic part. Because if I already know or I have already proved that it is a constant and I have to just write the expression, I may just take this standing wave to be flat at a given instance, and I may only write the maximum kinetic energy of all the particles. That means I'm deliberately writing the expression of energy at a time instance when I knew that the potential was zero. So I've written the kinetic and I'm equating it with the total energy. But that is only after knowing the fact that it is a constant. But if you are proving it, you need to write justify through this expression only that why is it a constant. So once you analyze it, I mean, after this, it is primarily maths only. Any expression, variation with time, it is constant with respect to time or not, how much is passing from a particular location. All these answers are actually in this expression only. That is the dE expression of that dx segment at any t is equal to t. That is what I have encircled. Even when you look at nodes, I mean, that way also I can explain. Even if you look at nodes and you look at different instances, the v velocity part as such, that will remain zero, right? Because, I mean, that particle is at the same y location. But if you look into the slope there, that keeps on changing. So I think all of us understand that when we talk about nodes, that if you look into these two nodes, let's say consecutive nodes I'm talking about, and we look into position when it is flat. And then I look into the signal after some time, which is like this. So if you look into the antinode position, the slope there is always zero. So the potential energy in that segment, that remains zero. And kinetic energy keeps on changing. Obviously keeps on decreasing as we move like this. And if you look into the potential of this point, potential energy located here, so the slope keeps on increasing, so that potential energy stored in this segment keeps on increasing. So we understand that when a standing wave is being formed, if you look into the energy pattern, it's like the interaction of energy between node and antinode, where one of them is decreasing its kinetic and the other guy is increasing its potential till it attains the maximum potential energy at this state. And this guy is spreading energy in both the directions. So when we talk about his own energy, crossover energy from this cross section, that becomes zero. So ultimately, antinodes are guys who are supplying energy to the nodes while they are moving from their mean position to the extreme positions. And this guy and all the intermediate guys, now at any instance, if you want to write the exact expression, we have the expression here also. But on the basis of the analysis that we have done on the expression, I am making the statements. That at all the locations which are intermediate also, if you talk about the energy, it is getting converted. I mean, there is a variation in the kinetic as well as the potential energy at all the cross sections. Through this expression, we can observe. But these two boundaries are very categorical. No kinetic energy here ever, only the potential variation, and no potential here, only the kinetic variation. That also decreased, and this is increasing. So supplier and this guy will keep on receiving the energy. And the same is happening on the right side also. It is absolutely symmetric. Only the total is constant. That is also on the basis of this expression only. If you integrate this expression in the above case also, from x is equal to 0 to location lambda by 4, you will see that that expression won't come out as a function of time, because you will integrate assuming t to be a constant, but you will obviously get expression of sine square omega t plus phi and cos square omega t plus phi as such as a constant there, which will come out as 1, which will justify that that won't depend upon time. So the same thing I am using here while answering the question. If you observe all the ideas that I have given here, we can understand that Net flow of energy through the section OS is dependent on time. Yes, it will change. OQ, that is not changing. That is between node and antinode. OC, again, it is not changing. And OT, this part is constant, but CT will change. So it is actually changing. It is dependent on time. So D option here will be the correct answer. Any calculation of energy, this expression will help you out for energy as well as power expressions. This is a problem in which there is a uniform freely hanging rope with wave velocity v, which varies with the distance z from the top. And this is because the tension varies while the mass per unit length mu remains constant. Now, there is some hypothetical thing that we demand. The thing is, suppose you want to design a freely hanging rope in which wave velocity is independent of z. So, like I generate a pulse from the highest or the bottommost point of the rope, and it travels throughout with a constant velocity on the rope. So, if I want to design such a rope, obviously we know that mu cannot be a constant mass per unit length. So, first question is the same, that the desired form, what kind of density function, linear mass density function, should we plan to ensure that V remains a constant. Let me just draw it like this. If this is my wave string on which a pulse has to move, and he has already given that you have to take z is equal to 0 as the top, and let's say so positive z is in the downward direction, right? Some z is equal to 0. So when you say that it is independent of z, what kind of function it will have? So I think all of us can find out. Like, I mean, we can write. I'm talking about a general z. So v is equal to root of tension at that z upon mu as function of z and vz. So basically, we are saying that vz square mu z is equal to tz. That is my first equation. The rest, there are a few things which are also given. They have already mentioned that z is equal to 0 is a location where mu ka value is mu naught. So mu naught is the mass per unit length at the topmost point, and function is what I have to report. So we are very clear, as he has already said, that v is a constant. So dv, like dvz term, should be equal to 0. That is my second equation. One more thing that we know here is t, if I want to write expression of dt, I mean, dmg was the reason. So if you go to a general z and cut a dz element, and we understand that tension here is T, and here it is T plus dt. I'm taking downward direction as positive. So I'm getting dt plus dz. So it is like mu as function of z into dz into g, that is equal to 0. So that is maybe my third equation. So dt I'm getting as minus mu g dz. That is my dt in this problem. Now I think we can easily solve the question. Vz is a constant for you in the problem. dt is known to you. So I think you can directly write your dt as, now I'm not writing z again. So I'm simply saying it is v square, which is constant, d, v square d. Now I think easily we'll get this expression. This expression is known to us. So we are getting d mu upon mu as minus g upon v square into dz. And this is from 0 to z. And this is mu naught to general. If you solve this equation, I think you are getting ln of mu upon mu naught as minus g by v square multiplied by z. So mu comes out as mu naught into exponential of minus gz upon v squared. So that was A. Now he wants to make changes in the same problem. He says, if the total mass of the above string is m, that we can find. Right? This is exponentially decaying. So even if you go from 0 to infinity, it will have a finite mass. That mass is m. I'll use it. And suppose we take only a length L of this rope from the top, such that we can still have a constant wave speed. I mean, the same relation as we have used above. On the finite rope, obviously, this is a infinite rope with a exponentially decaying mass density for the speed to be constant from top to bottom. But now we want to make a length L of the rope only. And we want to ensure that in this segment, even if I take a L length, he is saying that hang a mass here separately, which is capital M. What should be that mass M if you have to hang it at a location L, such that even if we now generate a pulse, right, from z is equal to 0, it travels with a constant velocity till this point, from z is equal to 0 to z is equal to n. So my simple submission here is that in previous problem and this problem, the concept is similar. The only thing is, if we can generate tension functions which are of the same nature as the previous one, I will get the same result. And my only thing is, I indirectly perceive it like this. If you cut the above rope from L up to infinity, and whatever weight you were having, if that is the mass M here, then the tension that this rope has to generate at L will be generated here also. And after that, the rope is the same. So similarity will hold as such. So for me, if I read this question, I perceive it like this, that you are trying to tell me that M is basically integral mu as function of Z dz from Z is equal to capital L to Z is equal to infinity. This is my mu as function of Z in this problem, right? And what about the mass M in the previous case? So, I mean, M that he is giving me is actually integral of mu as function of Z dz again from Z is equal to 0 to Z is equal to infinity. Basically, these are the two equations that we need to use while solving the 10th question. Idea there is in this problem is simple. From capital L to infinity, he is cutting that segment of the rope and he wants the above tension distribution, tension variation to remain the same. So I'm just replacing it by equivalent weight. And this M is just given to, express answer in a simpler terms. So just you have to divide, I think, and you'll get your answer. And mu as function of Z is. So I don't think that will be a big hassle. Get your result. Okay. Let me take up this problem where he has given these three informations. Just check this carefully. Here a pulse is started at a time instance t is equal to 0 along the positive x direction on a long taut string, and shape of pulse at t is equal to 0 is given. I think there are a few parameters that he wants me to find out. Just check these parameters and try to answer the problem. Y as a function of x is given, and just he wants you to find out the shape of the string, area enclosed. Yeah, you have to find out the vertical displacement of particle and the transverse velocity at x is equal to 13 and t is equal to this much. You can verify these results which come out in this problem are like, let's see. Yeah, so this comes out as 2.5, that is 0.25, and 13th comes out as minus 250. So can just note down the result and solve or try on your own. More special. In this case, in the next problem, taken a different function. Just solve this case. At t is equal to 0, there is a transverse wave pulse which is traveling in the positive x direction, and the speed is given, which is 2 meter per second. And the wave is described by this function y is equal to 6 by x square. X is not equal to 0. So y is equal to 6 by x square. Let's see which segment he is interested in. This is x is equal to 0. So he's saying what is the transverse velocity of the particle at x. Now, what I want in this case is, I also want you to find out the energy of this signal between x is equal to 1 and x is equal to 2. So if this pulse, and I think you understand that you cannot include that point x is equal to 0 in this pulse. So if this pulse is traveling in the positive x direction with a speed of plus 2 meter per second, right? We want to write the expression of energy stored in the pulse at this instance. If this is the instance t is equal to 0, from x is equal to 1 to x is equal to 2. Although this question was that we can also answer that x is equal to 2 per t is equal to 2. What is the transverse velocity of the particle? So all of you can just go through that part also. And then the second additional part, which I want actually to solve in this problem. 1 se 2 mein, whatever segment of wave is there, you want to find out the energy stored in that segment. X is equal to 1 to x is equal to 2, and time instance t is equal to 0. And all other constant parameters are known to you. So the tension in the string, the mass per unit length, wave velocity is given 2. So you can use the constants as such. So we only need the expression in terms of those constants. You can use mu term also, which is uniform throughout. So maybe while I'm solving this, now let's see how should I go about it. So I will try to write the dE expression and integrate it in this problem. So it is half of mu dx, mu I am taking as constant, into particle velocity square. So Vp term. So minus of, it is plus 2 and dou y by dou x. So it comes out as minus 12 upon x cube. Right. So that is the kinetic term, plus it is half of tension T dx dou y by dou x. So again, minus 12 upon x cube, the whole square. So I've written half of t dx into dou y by dou x whole square and half of mu dx into dou y by dou t, the whole square, which is negative of wave velocity with sign into slope, the square. So now it's fine. So, I mean, the answer to this part will be only an integral of this part from x is equal to 1 to x is equal to 2. Secondly, that is one thing we can obviously find out. One more thing. If I want to just write the expression in the same problem of the rate at which the energy is getting transmitted, let's say from the location x is equal to 1 at t is equal to 0. So somebody sitting at this location is observing the power transmitted. Let's say the power transmitted from this location, x is equal to 1. So again, let me write the expression. So the same d I am going to write for dx, right? In terms of x. So I'm talking about that term d by dt now. d by dt. So d energy in that segment is known to me. And I think you understand, all of you understand, if this expression I've written as d, only I need to write the rate of change. And rate of change is basically because of rate of change of x coordinate at this location. And that is that is why the slope is changing actually. The slope is changing. So I think it will be straightforward for all of us because you can directly take the complete pulse to be moving forward. So simply use dE by dx into dx by dt, and that dx by dt can be represented by +2. So dE expression is known to us. dE by dx will be known, and just multiply it by dx by dt down. dx by dt is generally for the shape rate at which the shape is moving forward. So that is 2. So I think easily you can find out d by dt. That is the rate of transference of energy, the power at that particular cross section. So you'll get the answer to that problem. When an external agent will let a pulse move from top to bottom, the pulse will change its speed on the basis of the tension and the density. So it's like a root of tension upon density, linear mass density at different z locations. He said that I will devise such a hypothetical rope where v will remain a constant. So we thought that t upon mu should remain a constant. So I just wrote it as v square mu is equal to t. And I knew this thing that how tension is going to vary. Tension will change because of the weight. So I have gone to a general z. I have cut a element dz. I said tension here is t. Then at z plus dz, it is t plus dt. And there will be some weight of this section also. So there is some mu, mass per unit length. Mu as function of z into dz is the mass of this segment into g. That's the weight. I've just balanced the forces. So dt downward and mu dz g downwards, tt cancels is equal to 0. So I got an expression of dt. And I knew from this place that because dv is 0, v is constant. So I took dt as v square dv. I've just taken d both sides. So v square d mu it became, and that was equal to minus mu g dz. Then it was simple integral. I got mu as function of z. Then I said, he had given in that problem that at z is equal to 0, mu was equal to mu naught. So I used everything. Then he says that instead of using this infinitely long string having such a linear mass density function, we will take the same string and we'll cut it at z is equal to some L. And we'll, instead of the second part of string, we'll put a weld a mass small m, mass capital M at L is equal to capital L. Then what should be that mass capital M so that we can still have the constant wave speed on the finite rope. So I'm saying not only that, if you also want the same speed, that is also possible, because ultimately while the signal is traveling from top to bottom, what it observes at every location is the density function there and the tension there. Now tension at that location is dependent upon the weight beneath that point. So if I have got a rope and I'm writing tension at a location, that is actually equal to the weight of the lower segment. So if you wish to cut a segment of rope, what I'm trying to say, whatever is the mass of that segment, you try to replace it with a point mass capital M at the same location. By virtue of this, what is going to happen? At all the cross sections above, everywhere, tension will remain the same as the previous case, because like mass is same beneath that point. So that's what I have done. So I've integrated from capital L to infinity, and I say that is capital L. And small m was the previous mass that he has given in this case, where the rope was extending from 0 to infinity. Then I have just divided these two equations and I got a relation between capital M and small m. Here, again, he has given me a wave shape. So he said, y is equal to 6 upon x square. Obviously, this can represent a traveling wave for all the points except x is equal to 0. We understand that it is not bounded at this point. So while I have drawn the shape of the pulse, I know that I can treat this as a signal, as a wave, traveling wave, for all x points till x is equal to 0 minus, and from 0 plus to infinity again. So let's say this is the wave shape I have drawn here. T is equal to 0, it looks like this. And it is traveling in the positive x direction with the speed of +2. Now, I I did this additional part, but the actual question was, what is the transverse velocity of particle at x is equal to 2, at t is equal to... Let me also just quickly go through the derivation also. All of us understand that while we are writing a traveling wave, a plane progressive traveling transverse wave, we are looking at functions y, which are of the format f of ax plus bt, right? And we understand that the ratio of b and a represents the speed, and the relative sign represents the direction in which the wave is traveling. So we all understand that like particle speed, when you say that is dou y by dou t, and slope, that is basically dou y by dou x. So dou y by dou x is a f prime of that same function, and dou y by dou t is b f prime of that. So when you divide, particle speed I'm getting as b by a into the slope dou y by dou x. So that's what I was saying, that while if you look into this equation, effectively what we get is Vp is equal to negative of wave velocity with sign, the direction in which the wave is going, and multiply that by the slope. You can check that that comes out same as the previous expression, because b by a actually is this value on its magnitude is the wave speed. And what about the sign? So if it is moving in the positive direction, this will be negative. Both the signs will be opposite, which is what I am also getting. And if it is moving in negative direction, it will be positive. Both are of same. So that is the result I am trying to use. So when he said transverse velocity of the particle at x is equal to 2 at t is equal to 2, let us just try to answer this one. For me, at t is equal to 2, because it will travel a distance 4 rightwards. So by transformation of coordinate, it will become y is equal to 6 upon x prime square, and that is actually x minus 4 at t is equal to 2. So x minus 4 the whole square. So basically at 2, this is your wave equation. And obviously it will look like this. So x is equal to 4, and that is how it will look. This is how your wave will look at t is equal to 2. And you want to ask कि x is equal to 2 पर जो particle है, इसका particle velocity क्या है? So now I will simply use, to answer this problem, I will say it is negative of the wave velocity, so positive direction 2, so plus 2 into dou y by dou x. So just take d by dx of 6 upon x minus 4 the whole square. Find out its derivative of this expression and then substitute x is equal to 2. This should be the answer to the original question. तो इसमें से कुछ आ जाएगा, ये 3 minus 3 8 or minus 8, but this is this thing. And what have I done additionally in this problem while analyzing? I just wanted to say कि if he asked me to find out the energy also between a given segment, let's say from x is equal to 1 to x is equal to 2 at t is equal to 0. So at that t is equal to 0 instance, I went to x is equal to x, I cut a dx element, I've written the differential kinetic and the differential potential of the dx segment at t is equal to 0. And if I add those energies and integrate it from 1 to 2, I get the total energy between 1 to 2 at t is equal to 0. So that can be one question. Secondly, what I was interested in, if somebody says that you find out the rate at which the energy is crossing any cross section, x is equal to x, at that instance t is equal to 0. So what I was trying to tell is, you know the differential energy which is stored there, right? D which is stored there, and its rate of change effectively tells you the rate at which it is getting transferred, the rate at which it is coming, or whichever way you perceive it. So the rate at which it is coming is the rate of change of the energy which is stored in the dx segment, and this is the energy. So I wrote dE in dx and then just tried to write dx d upon dt. So I simply said that you do dE by dx and try to do dx by dt. That dx by dt indirectly represents this signal speed, because all these cross sections are moving forward. at the same rate. So the power transference is something which can be easily perceived. If you write dE expression correctly, you can obviously write the rate of flow also from that cross section. So indirectly, what we are saying is dE by dx itself is some function of x. You can observe here, right? If you just eliminate that dx, it is a function of x. I think you got the idea. I was explaining the same key. dE जो है वो, it is a function of x at every dx segment. And if you know the energy in every dx segment at any t is equal to t, because this I'm writing at t is equal to 0, no? For this specific case, but I could have written this for any t is equal to t. Obviously, you understand that all these calculations I'm doing in this problem are for t is equal to 0 only. But generally, if you give me expression, I know everywhere I will have an expression of a t term is also involved there. Okay, fine. So I'll just try to finish off now and we'll meet in the next class. Take care.